In this work, we present TrafficSim, learning to simulate realistic multi-agent behaviors. Simulating realistic traffic scenarios is a critical step towards enabling safe and scalable self-driving. It allows us to generate testing scenarios at scale and augment training data for autonomy models. To build a realistic scenario, we need to first place traffic actors on a map, then simulate their motion forward, and lastly, render the environment. In this work, we focus on the second step. Existing simulation environments rely on manual scripting or heuristic model that directly encode traffic rules, and thus cannot capture the full range of naturalistic driving behaviors seen in the real world, such as U-turns and merges. On the other hand, deep motion forecasting models learn naturalistic behaviors from human demonstrations, but suffer from compounding error when on road in closed loop for simulation. Imitation learning techniques have been proposed to mitigate such compounding error, but the most popular approaches require either manual data augmentation or difficult adversarial optimization. Thus, we propose TrafficSim, which aims to combine the best of these three worlds. In our simulation environment, we consider as input a map, traffic control, and some initial actor states. We use a graph neural network-based joint actor policy to capture interaction between all actors in the scene, and then update the simulation environment in a differentiable manner. For learning, behavior cloning is insufficient for simulation, since the policy only observes ground truth states during training, but encounters novel simulated states when on road. This results in compounding errors that quickly drive actors off the road. In contrast, we unroll the policy to observe simulated states induced by it, and then backpropagate through our fully differentiable simulation across time for learning. Furthermore, we augment this imitation learning objective with common sense by incorporating an additional differentiable collision loss, and also introduce a time-adaptive multitask loss that downweights the imitation objective through the simulation horizon. Our model is able to handle a large number of actors in the scene and is adaptable to a wide variety of map topologies. Furthermore, our model is efficient and allows us to generate a large number of scenarios scalably. Now, let's take a look at the actors in detail. In this first example, the actor nudges past a parked vehicle partially obstructing its lane. Here, the actor first yields for oncoming traffic, then performs a U-turn. In this scenario, the actor slows down for a parked vehicle ahead, then waits for a nearby actor to pass, and finally lane change to make progress. In this last scenario, the actor yields for oncoming traffic before performing an unprotected left turn at the intersection. In comparison to motion forecasting baselines, our method is much more robust for simulation over long time horizon. It generates realistic actor behaviors, avoids collisions, and follows traffic rules. Here, we see that the heuristic-based IDM model also avoids collision and follows traffic rule. However, the actor behavior it generates is a lot more rigid and unrealistic compared to our model. Looking at the results, TrafficSim achieves the lowest scenario collision rate and scenario reconstruction error, and finally achieves traffic rule violation rate similar to that of human. To evaluate the realism of our simulation, we train a neural planner to imitate simulated actor trajectories and then evaluate it on real scenarios. We find that the planner trained on TrafficSim scenarios achieves similar performance as planner trained on real data, whereas other methods are much worse. In conclusion, we have presented TrafficSim, a multi-agent behavior model for traffic simulation. We leverage a graph neural network-based architecture to capture interaction and use closed-loop training with differentiable simulation and auxiliary objective for robust simulation across time. Thank you for listening.